It all began with a simple little bean, the Calabar bean. It was a beautiful purple bean when I first got it. But it is not only beautiful in its appearance, but also in the laboratory it has within it.
From the Calabar bean, chemists had isolated physostigmine, an alkaloid used to treat glaucoma. But by 1932, no one had yet been able to synthesize the molecule. Robert Robinson at Oxford University had published 9 papers on physostigmine and was getting close to a final synthesis. But chemist Percy Julian felt there was a simpler approach with fewer steps. However, physostigmine was a complicated molecule.
It bristled with spots around the molecule where methyl groups were hanging. That's a carbon with 3 hydrogens. There are actually 4 of these. And getting them in the right place is essential to making nature's molecule. It was a formidable chemical challenge for anybody to tackle in the early 1930s.
And Julian would tackle it step by step.
When you synthesize a molecule, you start with very small substances you can buy or that you know how to make already. You then start assembling those into fragments of the thing that you're hoping to make in the end. They're called intermediates. And what you're doing is you're following a particular path. This path takes you from the simple starting substances all the way to the final product, the natural product.
Along this path, Julian would choose from an array of procedures to manipulate atoms.
One can heat something to a very high temperature. That usually gets the atoms vibrating and makes new bonds possible. You can oxidize something, you can add oxygen to it. You can take oxygen out of a molecule, that's a reduction. We can expose it to pressure. Sometimes we can expose it to light to cajole the atoms to do what we want.
After each procedure, Julian needed to confirm that the intermediate compound made was what he intended. To do this, he would use a mechanism called a combustion train.
This technique takes an organic molecule which contains carbon, hydrogen, nitrogen, oxygen, and burns it.
Julian would weigh the released gases to find the amount of each atom present in the compound.
How much carbon does it have? How much hydrogen does it have? How much nitrogen does it have? If your compound has the right ratio, you're a long way towards being sure you've made what you thought you made.
And then you repeat this process of purification and of analysis for each intermediate until you finally get to the natural product.
It requires stubbornness. It requires focus. It requires repeating over and over the same kinds of processes until the answers come out.
After years of making and testing intermediates, Julian and fellow chemist Joseph Pickel synthesized their final compound. But in 1934, Robinson published his final paper, beating them to the chase.
He's done it! Suddenly my eye caught something. Look, Joseph, he's made a big blunder.
Julian noticed that Robinson's compound had a different melting point from its natural counterpart. To prove that their compound was indeed physostigmine, Julian and Pickel would need to take one final melting point.
When chemists took a melting point, they would put some crystals into a capillary tube, strap that capillary tube to a thermometer, and then place the complete assembly into an oil bath. They're looking to determine the exact moment when the crystals begin to melt.
133, 134,
Melting.
135, 136.
Finished!
Julian had proved that his compound, without a doubt, was physostigmine. The pathway he uncovered was an early example of total synthesis, the complete assembly of a complex molecule from simpler, more readily available substances.
Julian's pathway to physostigmine is so simple that it can be summarized in essentially 2 publications. Chemists look at them and marvel at how did he do that in so elegant of a